The second section of this unit is on radioactivity and nuclear chemistry. So, in order to understand nuclear chemistry and therefore what radioactivity is, we first need to understand or remember what are the essential parts of the atom. Okay, we've learned this in the past, but it's important that you remember what are the particles that are actually forming the nucleus of the atom. That is the core idea of, or is the basis of how nuclear chemistry works. So as you've learned before, the atom has two types of subatomic particles in the nucleus, the protons and the neutrons. And around the nucleus, it has the electrons that are orbiting around the nucleus. Let's take a look at each of these particles in specifically, more in detail. Okay, so the protons, as I said, are particles that are in or located in the nucleus of the atom. They're positively charged particles, and the charge is going to be opposite as the charge of the electron. Okay, the electron has negative charge, the proton has a positive charge. The mass of a proton, so how much it weighs informally, would be 1.0073 AMUs. And AMUs is not more than a unit, okay? It's atomic mass unit. Now, what does this mean? This means that it's 2,000 times bigger in terms of mass than the electron. How do we measure the number of protons that we have in the nucleus? We measure it with the atomic number. And this is a very important thing that you need to learn. Okay, the atomic number. The atomic number is represented with the letter Z, and don't forget that. And again, its number is the number of protons that are in the nucleus. Okay, the atomic number is really important because the Z, the number of protons, is what actually identifies the elements. There's no two elements in the periodic table with the same atomic number. So each of them have a specific atomic number and a specific amount of protons. Now, the other particles that we have in the nucleus are the neutrons, and the neutrons are neutral in terms of charge, so they don't have any charge. Okay, so it's a neutral particle and is found in the nucleus, and the mass of the neutron is very similar, very similar to the mass of the proton. Okay, so it's 1.0087 AMUs. Okay, the number of neutrons that we have in the nucleus determines the isotopes of the same element. We're going to be talking about isotopes very soon, okay? But the isotopes of the same element are determined by the number of neutrons. And then we have the electron. And the electron, as all of us know, is the particle that is orbiting around the nucleus. It's negatively charged. It has negative charge, okay? And it occupies a 3D region that is located around the nucleus called orbital. Okay, we're going to talk about orbitals in the near future as well. Okay, the orbitals are the most probable location to find the electrons in the atom. Okay, the mass of the electron is way smaller than the mass of the proton. It's 5.5 times 10 to the negative fourth. Okay, so it's more or less 1/2000 the mass of the proton. And the electrons are the responsible of the chemical reaction, so they are involved in the chemical reactions. Okay, so again, we have the protons and the neutrons in the nucleus, and the electrons around the nucleus in orbitals. In the atom, the nucleus makes a very small part in terms of space that it occupies. Okay, the size of the nucleus of the atom is very small in comparison with the size of the atom itself. The electrons are around the nucleus, and as I said, they are describing, or they are moving in 3D regions that are called orbitals. We're going to talk about orbitals later on, okay? But the orbitals are around the nucleus, and they are 3D dimensional clouds where it's the most probable location to find the electrons. This is a chart that is important that you learn because it has important content and information, and it's not difficult to memorize. The particles that we have learned so far are the proton, the neutron, and the electron. You need to remember that the proton is in the nucleus and the charge of the proton is +1. Okay, the mass of the proton in AMUs, it's going to be more or less 1, so it's 1.0073. And this is important for now and for the future. The proton could be represented in two different ways. You can represent it like a hydrogen atom, like this, a hydrogen with a 1 and a 1 as Z and A. You will learn what that is later in this set of notes. or the proton could be represented like P+. Both symbols are important for you to learn and understand that those are protons. In this set of notes, the symbol that we're going to use the most is going to be this one, the P+ symbol, but you also need to understand that the proton could be represented like H and then one on top and one at the bottom. I will tell you what that is soon. The second particle or subatomic particle is the neutron, which we know it's in the nucleus. It has a charge of 0 because it's neutral, and the mass, remember, is similar to the proton, so it's 1.0087. And the neutron, again, could be represented through two different symbols. One could be a 10N, like this one, or the other one could be like N and a superscript of a 0. Okay, both of them are ways to represent the proton, and you need to know how to use them. In this unit, we will use the first symbol more than the second one, but still you need to know or identify both symbols. And the third subatomic particle, again, is the electron. The electron is located in the 3D regions called orbitals around the nucleus, okay? The charge of the electron is -1, the opposite charge as the charge of the proton. Its mass is very, very, very small, so 0.00055, okay? And the electron also could be represented in two different ways. It could represent it like this 0, -1e, or E negative. Both of them are valid. You need to know both of them. In this unit, we will use more the first one, and I will show you why, because it's going to be related to radioactive decay. But the second symbol, the E-, I use it a lot as the representation of the electron. So again, make sure that you understand and you learn the symbols for the three subatomic particles, because you will see them very often in chemistry. Now, the elements in the periodic table, right? So how do we differentiate one element from the other one? Well, the way we know that one element is itself and not another element is because it's atomic number. We said that before, okay? The atomic number is going to be represented with the letter Z. So anytime you see Z, that means atomic number, okay? A capital Z. And the atomic number, as we said, is the number of protons that is located in the nucleus of an atom. It defines the elements. Again, in the periodic table, there's no two atoms that have the same atomic number. Each atom has a specific atomic number, okay? All right, so now you should go to the periodic table, take your periodic table. I am posting the periodic table in Google Classroom. You should always have a periodic table when you're working in chemistry. And let's figure this out. The first question says, which element has 35 protons? Well, if you go to the periodic table and you check the atomic number of 35, you will understand that the element that has 35 protons, so has a Z of 35, it's bromium, okay, Br. And what element has a Z of 12? So which element has 12 protons in the nucleus? So again, you go to the periodic table, you find the atomic number for in the number 12, so the number 12 has the atomic number, and you will realize that we're talking about magnesium here. How many protons and electrons does the element whose atomic number is 8 have? All right, so you actually have a hint here in this slide. The element that has 8 protons, that has an atomic number Z, an atomic number of 8, it's oxygen, okay? So the question is, how many protons and electrons does the element whose atomic number 8 is 8 have? So because oxygen has a Z of 8, it has 8 protons. And if they don't tell us that oxygen is an ion or that is charged, we assume that it's neutral. So that's why it's going to also have 8 electrons. When the atom of an element is not neutral, so when it has charge, we call it an ion, okay? Right before the explanation of the ions, we have learned about the elements. If it doesn't tell you anything about an element having or an atom having a charge, you take for granted that that atom is neutral, that it has the same number of protons and electrons. But sometimes the atoms do actually have a charge because the number of protons and electrons is unbalanced. So that's what we call an ion, okay? So an ion is an atom that has gained or lost electrons. It's all about the electrons, okay? About losing or gaining electrons. The protons stay the same because the proton is what identifies the atom. So do not think that an ion is formed by the addition or subtraction or losing the protons. It is always, always, always by gaining or losing electrons. Now, ions, as I said, has a different number of electrons as protons. That's why it has a charge. So when the number of electrons is higher than the number of protons, that means that it has more negative charge than positive. So the ion is going to be a negative charged ion. And that is going to be called an anion. And all these terms are essential for you not to get confused for the rest of the school year. So make sure that you learn and memorize them. How do we represent the negative charge of an ion? We represent it with a superscript of a number that is going to be a negative number. Okay, so for example, oxygen, when it becomes an ion, it becomes an ion because it gains 2 electrons. So the charge of the oxygen is going to be 2 minus. On the other hand, if we have ions that have been formed because they have lost electrons, so they have less electrons than protons, that is going to be called a cation. And cations have positive charge. And the way you represent the positive charge is the same as what you do with the negative one. You write the element's symbol, and then you write a superscript with a positive number. Okay, so for example, lithium, when it becomes an ion, it does it because it loses 1 electron, so it will be lithium plus 1. Okay, so remember, the protons and the electrons have a relative charge of +1 or -1. What's a good example of how a neutral atom becomes an ion? Well, the one that we have over here, the sodium atom. The sodium atom, it's a metal, it's in group 1, and it has 1 valence electron in its outer shell, okay? So when the sodium, for example, wants to get together with the chlorine or with other elements to form a salt, for example, what it does is it loses that outer electron. It goes away. So now the sodium has 1 less electron than before. If it has 1 less electron than before, the number of electrons is not going to be the same as the number of protons anymore. And now we have what we call the sodium ion. And because it has lost 1 electron, the sodium now will have 1 positive charge. And this is the sodium ion. Let's do some examples here to understand what we just learned. It says, write the symbol for a sodium that has lost 1 electron. Okay, so this is the example that we just learned. So the sodium loses 1 electron. It means that it has 1 less electron than protons. So the sodium is going to become sodium 1 plus. Again, the loss of electrons means positive charge. When I lose something negative, I get positively charged. Now it says, write the symbol for a magnesium that has lost 2 electrons. So magnesium, go to the periodic table, has a symbol that is Mg. And now it says that magnesium has lost 2 electrons. So the loss of 2 electrons leaves the magnesium with 2 positive charges because now the number of electrons is lower than the number of protons. Okay, so there's more positive charges than negative. That's why it's positive. Again, losing electrons means losing negativity. Therefore, the ion becomes positive. Okay? So again, losing electrons, ion, it's positive. Okay? So it's going to be any symbol with a positive charge here. Okay? And the positive charge is going to be based on the number of electrons lost. So if in the element is losing 2 electrons, it will be 2 plus. 3 electrons, 3 plus, 1 electron, 1 plus. Okay, so N plus in general. Now it says, write the symbol for an oxygen that has gained 2 electrons. So we saw that example before. Oxygen has a symbol of O. And now if the oxygen has gained 2 electrons, that means that it has gained 2 negative charges. So that means that now the charge of the oxygen is going to be 2 minus. How many electrons does fluorine have? Well, for this, you need to go to the periodic table. You will realize that fluorine, it's an element that has an atomic number of 9. Okay, this is again something that you find on the periodic table. Now, having a number of 9 means that it has 9 protons. 9 protons. See how I use the P plus sign here? That means protons. So that's for sure. That's not going to change because the 9 protons are what make fluorine be fluorine. Now, this fluorine over here specifically, it's fluoride because it has a negative charge. So having a negative charge means that this atom, which is an ion actually, has one more electron than the neutral one. The neutral one would have 9 because 9 positive and 9 negative cancel out. That would be 0, right? No charge. But in this case, as I said, there is one negative charge here. So that negative charge means that this atom has one more electron than the neutral one. So the answer to this is how many electrons does the fluorine negative have? It has 10 electrons, one more electron than what it would have if it was neutral. How many electrons does the calcium 2 plus have? We need to do something similar here. So we go to the periodic table and we find the Z, the atomic number for calcium, and calcium has a Z of 20. What does this mean? This means that calcium has 20 protons. That is what makes calcium be calcium. If calcium was neutral, it would also have 20 electrons. But here we see how this calcium is not neutral. It has a charge of plus 2. So what does a charge of plus 2 mean? It means that calcium in this case lost 2 electrons. So the overall number of electrons that this calcium 2 plus has is not going to be 20. It's going to be 2 electrons less than what the neutral calcium would be. So the answer would be 18 electrons. What are isotopes? Isotopes are atoms of the same element that have a different number of neutrons. In order to be atoms of the same element, they have to have the same number of protons. But what makes them be isotopes is that they have different number of neutrons, okay? And because they have the same number of protons, they belong to the same element, and the different number of neutrons makes them be different isotopes of the same element. So for example, hydrogen has 3 naturally occurring isotopes, okay? It has an isotope with 1 proton and 0 neutrons, then it has another isotope with 1 proton and 1 neutron, and then it has a third isotope with 1 proton and 2 neutrons. So pretty much what does this explain to us? That because all of them have only 1 proton, that one proton, that is what makes hydrogen be hydrogen. But then each of the isotopes have different number of neutrons. So this one has 0 neutrons, this one has 1 neutron, and this one has 2 neutrons. That's why these are the 3 isotopes of hydrogen. There is this PhET simulation that you might want to use, and this PhET simulation, it represents really well what isotopes are and how they work. So again, we're going back to the hydrogen. The hydrogen atom, the element of the hydrogen, has 1 proton, the one that you see over here, right? But depending on the number of neutrons that it has, it will be a different isotope of hydrogen. So if we actually look at the symbol of the hydrogen that has 1 proton, okay, it's going to be the hydrogen that has an A of 1 and a Z of 1. We're going to learn that later, okay? If we analyze the hydrogen, the element or the isotope of hydrogen that has 1 proton and 1 neutron, you will see how this number up here, which is the mass number, is going up to 2, and then the Z, which is the protons, the atomic number, still is 1. And finally, we have the hydrogen, the third isotope of hydrogen that is unstable. It will have altogether an A and a mass number of 3 and an atomic number of 1. So again, the atomic number does not change. If you actually look at the abundance in nature of these isotopes, check this out. I'm going to go back to the beginning. The hydrogen 1, which is the most abundant isotope in nature, is the isotope that we find the most, if we take example of 100 atoms of hydrogen, 99.98% are going to be this type of isotope. Okay, the second isotope of hydrogen is going to be only, its abundance in the nature is going to be 0.0115%. And the third isotope of hydrogen, we're going to learn that about later, it's unstable. And it's a it has a very small abundance. That's why here it says trace. If you want to use this simulation, it's fedcolorado.edu, and it's the simulation that is called Isotopes and Atomic Mass. I'm going to post this in Google Classroom so that you can use it and enjoy it. I was just showing you the different isotopes of the hydrogen and its abundance, right? So we're going to learn what that means and how that is important when calculating the mass of the average mass of an isotope in our planet. Okay, so as we said, the isotopes are I'm going to say the brothers or sisters of an element that have the same number of protons but different number of neutrons, okay? So what's the atomic mass? The atomic mass is going to be the total mass of an atom. And in order to find the atomic mass, we need to understand what steps we need to take. So for that, first of all, you need to understand the units that you use for the atomic mass. And the units that we use for the atomic mass are the AMUs, the atomic mass units, and this is not more than a unit to measure the atomic mass of an element, okay? One atomic mass unit is the same as these many grams, which is a very small number, 1.66 times 10 to the negative 24th grams, okay? And that would be more or less 1/12 of the mass of the carbon-12 atom, okay? So when we have to calculate the average atomic mass of an element in nature, okay, how do we do that? The average atomic mass of an element in nature is going to be calculated as the weighted average mass of all the isotopes of the element in nature, okay? So what you do is you take all the different types of isotope of that element that you have in nature, and you do some calculations that I'm going to explain next. And through those calculations and taking into account the abundance of those isotopes, you will calculate the mass or the average mass of that element, okay? So how do we find, or where do we find those masses? If you actually look at the periodic table, in the periodic table right underneath the element symbol, you will see the average atomic mass, okay? These are the average atomic masses of magnesium and chlorine, okay? Now, how do we calculate the average atomic mass? Well, listen up. You have to follow this equation that you have over here, this formula. This formula tells you that the average mass of an element, it's going to be its abundance in percentage, and I'm going to show you how to do that and how to find that, times the mass of that isotope, okay? Plus the abundance of the second isotope times the mass of the second isotope. If there was a third isotope, it would be the abundance in percent abundance of the third isotope times the mass of the third isotope, and so on. If you right now don't understand what I'm talking about, don't worry, because we're going to do a couple of examples to understand this, okay? So here's an example. You have silicon. So you go to the periodic table and you find silicon. All right. And the question is, check in the periodic table for the average atomic mass of the silicon, and then calculate the average atomic mass with the information that you're given over here. Okay. So if you actually go to the periodic table, you will find out that the average atomic mass of the silicon element is 28.09, or something very similar, depending on the periodic table that you are using. How do we calculate this average atomic mass? Well, we're going to use this formula that we have up here, okay? So for that, we're going to use the percent abundance of each of the isotopes. This is the percent abundance, and we're going to multiply the percent abundance of each of the isotopes by the mass of each of the isotopes, and then we're going to add that together, okay? All right, so if you want to do these calculations, this is how you should proceed. So if you want to calculate the average mass, okay, remember you do the percent abundance of the first isotope as a percentage, so it's going to be 92.23 over 100 times the mass of that one isotope, so times 27.976927, okay, plus, you see it over here, the abundance of the second isotope, okay, So 4.67 over 100, because it's a percentage, times the mass of that one isotope, the isotope 29 of the silicon. So times 28.976495. Plus, because there is a third isotope, the abundance of the third isotope, which is going to be 3.10 divided by 100, times the mass of the isotope of silicon 30, the third isotope. So that's going to be 29.973770. If you actually add all these numbers up and you plug those numbers in your calculator, the answer that you're going to get is 28.09. And then you can ask me, hey, Miss G, but why do I have to calculate or learn how to calculate the average mass of the elements if I actually can find them on the periodic table? Well, it's because you could be given the actual average mass of the elements, and I might ask you to find the abundance of one of the isotopes. Or I could ask you to find the specific exact mass of the isotopes. So that's why you need to know and learn how to play with the numbers here. Let's do another example. Very famous, carbon. Okay, so carbon has two isotopes. They're called carbon 12 and carbon 13. Okay, this is a different notation that we use for isotopes that is perfectly valid as well. So if I had to find the average mass, the average mass of the isotopes of carbon altogether in nature, what do? Same thing. First thing, I take the abundance of the first isotope, so 98.90. 98.90 divided by 100 times the mass or the exact mass of that isotope. So 12.000000. 1, 2, 3, 4, 5, 6. So I'm missing 1 0 here. I'm just using all those suffix. Plus the abundance of the second isotope in percentage. So that's going to be 1.10 divided by 100 times the mass of the second, or the exact mass of the second isotope. So that's going to be 13.003355. So if I add this together and I add up together, the answer is going to be 12.01. And if you actually look up on the periodic table, that's the average atomic mass of the element called carbon. So before I continue with the examples and I continue with the notes, I just wanted to show you what's the periodic table that I'm going to be using for the rest of the year. These are periodic tables that we can print, and they have a bunch of information that is important. And this is the color version, and I also have it in the black and white version. Okay, if you have the chance to print the black and white version, that would be great, because that allows you, that gives you the possibility to draw into color if you want to, but otherwise you can print this in color, and this is very useful, and it will tell you what are all the groups in the periodic table. It gives you a bunch of information. It tells you what's the average mass of each of the elements. As you see, this is what we're learning right now, right underneath the symbol of the element. It also gives you the atomic number of every single element right above. Okay, then you have the name of each of the elements here. You don't have to memorize the periodic table, but you certainly need to know how to use it. So make sure that you always have a copy of the periodic table next to you every time we are in chemistry. All right, so let's use the periodic table, and then let's do one more example on isotopes. Well, before we go into one more step forward in learning what isotopes are and how do you represent isotopes and how you write the symbol of the isotopes, okay? So it tells you, use your periodic table. So again, you can use this periodic table that I showed you over here, and for that, or with that, it says, what isotope is the most common isotope of nitrogen? Okay, so if you actually go here to the periodic table, nitrogen, let me make this a little bigger, nitrogen, it's over here, okay? So you see how the average atomic mass of the nitrogen is 14.01. So that means that the vast majority of the isotopes that are isotopes of nitrogen, or better said, the isotope that has the highest abundance, the highest weight in that formula that I just showed you before, it's going to be the one that has a mass that is closer to this number. Make sense? So that's why I would say, and I would respond here, that the isotope that is the most common isotope of nitrogen is going to be nitrogen 14. Nitrogen 14. And the next question says, what isotope is the most common isotope of fluorine? Same thing. You go over here and you say, okay, what is fluorine? Fluorine is here, right? Fluorine, it's in group 17. So the average atomic mass of fluorine is 19. That means that the isotope of fluorine that has the highest abundance, that has the most weight in these calculations that we just learned, it's going to be the one that contributes to this number the most. So therefore, the isotope of fluorine that is going to be the most common is going to be fluorine 19. All right, so now I'm showing you a way to represent isotopes, okay? So the isotope 14, I am representing this way, the isotope, sorry, nitrogen 14, and the isotope fluorine 19, I'm representing this way. But there's another way to represent isotopes, and it's what we're going to learn next. Before we go there, just check this out. When you're representing an isotope using this notation, what you're using here is the element's symbol. And why I am writing here the element symbol and then dash and 19? Well, the element symbol itself tells me the number of protons. Because if I go to the periodic table, I know, check it out, that fluorine has 9 protons, right? So the symbol itself is already letting me know that it has, the number of protons is going to be 9, okay? What does this number represent then? This is what we call, and we're going to learn it right now, it's called the mass number. It's called the mass number. So this number, 19, is going to be, as you see over here, it's going to be the number of protons plus the number of neutrons. It's going to be the protons plus the neutrons. So again, for nitrogen, we know that nitrogen, it's an element that has, you can see it over here, 7 protons. That's the atomic number of nitrogen. So the number of protons is going to be 7. And this is what we call the mass number. That is the number of protons plus neutrons, okay? And we're going to figure that out next. So to find how many protons it has, okay? Because in order to find the protons, it's very easy. You just need to subtract the number that you have here, the mass number, minus the number of protons, and that will tell you the number of neutrons. Sorry, I was looking for the number of neutrons. Anyway, this is one notation for the isotopes, okay? What's another way to represent isotopes that is equivalent, and you also need to know, is what we call the standard nuclear notation. Okay, so the standard nuclear notation is just a way to give you more information on what are the number of protons and neutrons on the isotope that this notation that you have over here. So this standard notation has 2 parts or 3 parts. It has the name of the element first, okay, that is not the name, the symbol of the element first. X is a general letter for the symbol of the element. It could be O, N, L, I, it depends on the element. And then on the top left, you will write what we call the mass number. And the mass number again is the number of protons plus the number of neutrons. Do not forget this, okay? So the mass number, this number here, represents the number of protons, P plus the number of neutrons. And then at the bottom left, you actually use, or you actually write, the atomic number. So what is the atomic number? The atomic number is only the number of protons. Okay, number of protons. So with this information over here, this notation called the standard nuclear notation, you can calculate how many protons, neutrons, and electrons an atom has. Okay, and that's what we're going to do next. But again, do not forget that the Z represents number of protons and the A represents the number of protons plus the number of neutrons. Okay, and this is the standard nuclear notation. Based on this, on what we learned, let's actually figure this example out. Okay, it says write the standard nuclear notation for the following. The first one is going to be an atom with 8 protons and 9 neutrons. Okay, so remember, the protons determine the element, okay, what kind of atom it is. So you go over here and you say, okay, what's the atom that has 8 protons? What's the atom that has an atomic number of 8? That's going to be oxygen. Okay, that is going to be oxygen. So once I know that this is oxygen, I'm going to just move the periodic table here to the side. Okay, now that I know that it's going to be oxygen, the symbol is going to be O. What do I know next? I know next that as we learned, on the standard nuclear notation, the number of protons goes down here. So this 8 is going to go down here, like an 8, okay? And now, what are we missing from the standard nuclear notation? We're missing the mass number, the number of protons plus neutrons. So what do? I add these two numbers together. These two numbers added together adds up to 17, and that is what we call A, the mass number. So then I'm going to write a 17 up here. Let's do another example. So we have an atom with 15 protons. So 15 protons is going to determine what the atom is, the 15 protons, and 15 neutrons. All right, so let's go back to the periodic table over here. Let's make this periodic table bigger. And so what's this atom that has 15 protons? So 15 protons, keep in mind that the atomic number goes in order, so it's not difficult to find the number 15. See, 1, 2, 3, 4, 5. Okay, so 15 is going to be here. So 15 protons is the element that has 15 protons is phosphorus, P. Okay, so I go ahead and write P here. So phosphorus. And then I know that it has 15 protons, so I'm going to write the 15 down here because that's the atomic number. Okay, and then for the mass number, remember I have to add the protons plus the neutrons. That adds up to 30. So then 30 is going to be the mass number that goes up here. Okay. Now, an atom with 34 protons and 38 neutrons. So 34 protons and 38 neutrons. So again, I go back to the periodic table and I say, what's the atom that has 38 protons? What is the atom that has an atomic number of 34? So 34, it's here. So that's going to be selenium. All right, so I go to my activity over here and I write selenium, and that's the symbol for selenium, Se. The 34 protons go here, and then I add 34 plus 38, and that's going to be a total of 72. So I will write 72 on the top left corner. Now, if I actually would like to use the other notation that I learned before, so if I want to use this notation here, how do I would represent these isotopes? Really easy, okay? The oxygen that we see over here, instead of represented like this with the standard nuclear notation, this would be O and then 17. Okay, so both notations are correct and you should know both. The phosphorus would be P30 and the selenium would be Se72. Again, this notation that I'm writing here in green is just it takes for granted that you know that the element's symbol is going to tell you the number of protons. So it only shows you what we call the A, the mass number here, here, and here. Okay, so both notations are correct and you need to know how to use both. More examples, but now it's a little bit more complicated because we have ions here. Okay, so it says how many protons, electrons, and neutrons do the following atoms have? All right, so the first one, it's not an actual atom, it's an ion. Okay, so this one is an ion. Actually, all of them are ions. So this ion is the potassium cation because it's cation. It's a positive ion. A positive ion represents that electrons, in this case I'm going to write it here, okay? Positive means that electrons are lost. How many electrons are lost in this case? Well, if there is one positive charge, that means that in this case, one electron is lost. Okay? So now, if we know that, let's continue with the rest of the activity, just following what we have done before. How many protons does the potassium have for this notation? Well, 19 is the number of protons, is the atomic number, so the answer would be 19. How many neutrons, I'm going to go to the neutrons, does this have? Well, for this, you just need to do 39 minus 19, and that will give you the answer. Because remember, 39 is the mass number, and the mass number is the number of protons plus neutrons. So if you remove or you subtract from that the number of protons, that will give you the neutrons. So the answer is 20. And finally, let's go back to the electrons, okay? We said that the potassium has one positive charge, so one electron has been lost. That means that instead of having 19 electrons like the neutral atom would have, in this case it has 18 because it has one less electron than what the neutral atom would have. Remember, the neutral atoms have the same number of protons and electrons. Next one, oxygen, 2 minus. So, number of protons is given by the atomic number, okay? So that's going to be 8. Number of neutrons is going to be the mass number minus the atomic number, so 15 minus 8. And that's giving us a number of neutrons of 7. And finally, electrons. Remember that if the charge is negative, okay, in this case, the electrons are gained. How many electrons are gained? The number of charges that you have here. So 2 electrons have been gained. So this element, originally, if it was neutral, it would have 8 protons and 8 electrons. But the thing is that it's not neutral. So it has 2 more electrons than the neutral one. So what do we have to do? You need to add 2 electrons to these 8. So the total number of electrons is going to be 10. And finally, the copper 2 plus. So the copper 2 plus has a charge of plus 2, meaning again that 2 electrons have been lost. Okay, that is what the charge means. So the protons are going to be given by the atomic number, 29. The neutrons are going to be given by the mass number minus the atomic number. So the number of neutrons is going to be 36. Okay, 65 minus 29. And finally, the electrons again, because we have 2 positive charges here, so 2 electrons have been lost. That means that we have 2 less electrons than protons. So that's going to be 27, because originally when this atom was neutral, the number of electrons and protons was the same. So now that it's not neutral, it lost 2 electrons. The number of electrons is 27. So now that we have remembered what are the subatomic particles in the atom, let's focus on nuclear chemistry. And nuclear chemistry is the chemistry that happens in the nucleus of the atom. So therefore, we're going to focus more on what happens to the particles that are in the nucleus of the atom this time, okay? Now, all that nuclear chemistry explains, which is a lot, is the changes in the atom's nucleus, okay? It doesn't pay attention to what happens to the electrons. It only pays attention to what happens to the nucleus of the atom. So a nuclear reaction, which is in a specific type of chemical reaction, but it's the nuclear reaction, and that word is key. It's a reaction that involves a change in the atom's nucleus. So the atom's nucleus is going to change, and through that change, the reaction is happening. So what's going to happen? What's going to happen is that the atoms of one element will change into the atoms of another element. It's kind of magic, but it is. It happens. One element changes into another one. It's called transmutation, okay? So to understand nuclear chemistry and to understand how the nucleus gets either disintegrated or we have different types of decay or those nuclear reactions we were just talking about, first we need to understand what are the forces that hold and act on that hold the particles in the atom together or are acting in the nucleus, okay? So we have 2 forces. We have, first of all, what we call the strong nuclear force, and that's going to be the force of attraction between the nuclear particles. So it's going to be the attraction between the protons and the neutrons in the atom, okay, as they are close together. So there's going to be a force that attracts the protons and the nucleus together. So it's going to be a force that is holding these protons and these neutrons together, and that's called the strong nuclear force. But at the same time, there is another force that is acting on the nucleus, and that second type of force, or that second force, is called the electromagnetic force. And that force is opposite to the strong nuclear force, and it's a force of repulsion, not attraction. It's a force of repulsion. And it's a repulsion that happens only between the protons, that all of them have positive charges. So in this case, this proton, they repel each other. And that force of repulsion, it's called the electromagnetic force. So the strong nuclear force and the electromagnetic force are forces that are opposite. So in order to keep the atom together, those 2 forces must be balanced, Okay, keep that in mind, because if they're not balanced, if the strong nuclear force or the electromagnetic force is higher than the strong nuclear force, the atom's nucleus is going to fall apart. Now, the size of the nucleus, so how many particles it has in it, okay, and the ratio neutrons to protons will determine how stable that nucleus is, okay? We were talking about stability and how a nucleus is stable when the strong nuclear force and the electromagnetic force are actually balanced with each other, but the size of the nucleus, so how many particles we have in the nucleus, and what's the ratio protons to neutrons, that is going to determine the key word here, which is the stability of the nucleus, okay? So how do we determine the stability of the nucleus? We actually can read and we can see the data and learn how to determine whether a nucleus is stable or not by something called the band of stability, okay? And the band of stability could be represented in many different ways. There's many different bands of stability that different people have created, but all of them show the same. So the one that I'm going to be using, it's the one right here. It's the same as the one on the left. It just shows you the data in a way that I like it better because of the coloring. That's it. So what's the band of stability? The band of stability, it's this diagram that you see on the right and left of the slide, and it tells you whether an isotope of an element is stable or not, whether that nucleus is stable or not. So the first thing that I want you to pay attention to is the black line. It's not the black line, the black section, okay, that determines when an isotope is stable. So if you see over here in the center, I'm just marking that with my pen a little harder, we have a section on the band of stability that is marked in black that goes all the way to the number of neutrons N 126 and the number of protons 82, which is going to be what we determine as the stable nuclei. So anything within that range is stable. Now, if the ratio protons to neutrons falls outside the band of stability, so it falls either in this area or falls in this other area, then we're going to have an unstable nucleus, okay? So again, the band of stability is the section that you see over here that shows you the ratio protons to neutrons, and as long as this ratio is falling in this black section here, that's going to be unstable nuclei, okay? But anything that is outside that, like below or above, that's going to be unstable. So all the colors that you see here, the rest of the colors that you see here, these ones over here, the orange, the blue, the yellow, etc., all of them represent ratios proton to neutron in an atom that are unstable. So that's why it says the band of the stability, it says stable nuclei are found here and have a ratio of neutrons to protons high enough to keep the nucleus together. And that ratio, again, needs to fall in this black line that I just marked. Now, continue with the band of stability, okay? Any nucleus that is outside the band of stability, as I told you, the band of stability, I'm going to mark it again, is this black area here. Okay, anything outside that black area is going to be considered an unstable isotope. It's going to be unstable. When an isotope is unstable, it undergoes radioactive nuclear decay. Why does it do that? Because it wants to gain stability, okay? The isotope's nuclei want to be stable, but if they're unstable, they will release decay and they will try to become stable eventually. What's that radioactive decay? Those are the particles that we're going to learn next, alpha, beta, positron emission, etc., that the atom releases, or the energy that it releases, like the gamma radiation, okay? Now, the band of stability ends in, it says over here, bismuth 209, which has 83 protons and 126 neutrons. If you check it out, when you have 82 or 83, it's around that area, protons and 126 neutrons, this is the last last ratio, okay, that is going to allow you to have a stable nucleus. Anything above that, it's unstable as well. So that's why it says that the band of stability ends in the bismuth 209, okay, because that's the last element that can actually be stable. After bismuth 209 in the periodic table, and let's go to the periodic table now so that you can see that, as after bismuth 209, the any isotopes that you're going to have over there are going to be unstable. Okay? All right. So when an isotope is unstable, we just said that what it does is undergoes radioactive decay. And that radioactive decay can go in the shape of particles or energy. What are those types of radioactive decay that we need to learn, and you're gonna hear about this forever and ever in the future? Those types of radioactive decay, they're gonna be the alpha decay, beta decay, positive or negative, gamma radiation, and positron emission. We're gonna go into detail for everyone and each of these in a minute. As you can see in this diagram over here, not all of them carry the same energy. Okay, so the alpha radiation is the one that has the lowest energy. That's why we can stop it with a piece of paper. And then the gamma radiation is the one that has the highest energy, and that's why even though we have a piece of paper, a hand, water, and concrete, it will still go through because it's high energy radiation, very dangerous, okay? The higher the energy, the more danger it has. And then in between, we have the beta radiation and then the neutrons or the positron emission. You're going to learn that in a minute. All right. So what you need to understand again is that different types of radiation carry different energy. That's what I just explained. And therefore, they will be able to penetrate different materials. And the more they penetrate, that means that they have more energy and more dangerous they are. Before I go into each of the types of radioactive decay that we're going to learn in this unit, let's explain what a nuclear equation is, because nuclear equations are actually the equations that represent what happens in nuclear chemistry, and they actually tell you what happens to the nucleus of the isotope that is going to transmutate into another isotope, so change into another isotope, and therefore it's going to also tell you what kind of radiation it's going to release. Okay, so the equation represents the radioactive decay, that's the nuclear equation, and what's going to happen is that the charge, okay, the atomic number, and the mass number will be conserved, okay? So that means that the atomic number and the mass number at the beginning of the reaction in the reactants and in the products altogether should be the same. For example, we have the nuclear equation of the carbon isotope, the carbon-14. As you can tell over here, you have the carbon-14 that is going to be releasing a particle. We're going to learn what type of particle this is. This is a beta particle, okay? And it's going to transmutate, so it's going to change into a nitrogen isotope. Isn't this magic? So one element turns into another one. Okay, so this conservation of the atomic number and the mass number means that if the atomic number of the carbon originally was 6, the addition of this atomic number and this atomic number, it should be 6 as well. So it's conserved. And if the initial mass number was 14, the addition of the mass numbers of the particle or the transmutated new isotope altogether should be 14 as well. So that's why we say that it has to be the same on both sides, okay? Keep that in mind. That's important so that you know how to do nuclear equations later on. So again, one element releases a particle and becomes into another element. And the A, so the mass number, and the Z, the atomic number, will be conserved. The first type of radioactive decay we're going to talk about is the alpha decay. So alpha decay, or alpha particles, are represented with the letter alpha, and the letter alpha is this letter that you see over here. Okay, it's written like this. But also alpha particles are represented like a helium nucleus, and it's a helium nucleus that has 2 protons and 2 neutrons. If we actually remember what we just learned on the notation of how to show isotopes, this is the notation for the helium nucleus that has 2 protons and 2 neutrons, so altogether in mass number of 4. So again, alpha particles are represented like or using the letter alpha or as a helium nucleus. Okay, a helium nucleus that has 2 protons and 2 neutrons. The alpha particles don't have a lot of energy, and because they don't have a lot of energy, they do not penetrate well, okay? So therefore, they can easily be blocked by any thin material such as paper. Now, when there is alpha particle emission, this is what is going to happen to the original radioactive isotope. What's going to happen is that the radioactive isotope is going to lose 4 units in the mass number, and it's going to lose 2 units in the atomic number. Example, we have this example over here. So we have a radioactive isotope over here. The radioactive isotope has an atomic number of 88, so 88 protons, and a mass number of 222. So when the radioactive isotope releases an alpha particle, it transmutates or changes into another isotope. And that isotope, because it has released a particle that has 2 protons, will have 2 protons less. And then, because the particle that was released, that alpha particle, has a mass number of 4, the new isotope will have 4 units less in the mass number. Okay? So just to repeat, to review, if we have a radioactive isotope that emits alpha radiation, when it emits the alpha radiation, that is going to be emitted as a nucleus of helium. Nucleus of helium, it's going to be helium-42. So therefore, the new isotope that is being formed is going to have a mass number of 218 and an atomic number of 86 in this case. Now, if you actually look at the nuclear equation here, remember how the atomic number and the mass number were conserved? Keep this in mind. Every time you have a nuclear reaction like this one, if you actually add the atomic numbers of the products, they will have to add up to the original atomic number. And if you actually, I'm going to say it in just another color, and if you actually add the mass numbers of the 2 products, those are going to add up to the mass number of the original radioactive isotope. So that's the way that you can find out what is the new radioactive isotope, or you can find out what's the particle that is being released. The second type of radioactive decay that we're going to learn is called beta decay. And the beta decay has, I'm going to say it represented in 2 forms as well, and both are valid. One, it's going to be the beta negative symbol, that is beta decay, or the other one is going to be represented as an electron, okay? And an electron that has a 0 as the mass number and a -1 as the atomic number, okay? So these 2 forms or these 2 symbols are representative, or they show what a beta particle is, which is a high energy electron. Okay, the beta particles are smaller and lighter than the alpha particles. They move faster, and they can pass through matter more easily, meaning that they're more energetic, they have more energy than the alpha particles. So they're smaller, lighter than the alpha particles, and they move faster. They penetrate easily or more easily than the alpha particles. Now, in order to stop them, because they have more energy than the alpha particles, we need thicker materials. Okay? Now, when the beta decay happens, the electron produced or will be produced when the neutron changes to a proton. Okay, so when one of the neutrons in the mass number changes into a proton, okay, as a product. I'm going to explain this to you in a minute. This is not going to be an electron from the outside of the nucleus. So the result is going to be that they will have the same mass number, so same A, and there's going to be an increase in the atomic number by 1 in Z. Example, we have another isotope here. In this case, it's a very famous one because it's the isotope of carbon, carbon-14, right? So carbon-14 has 6 as an atomic number and 4 as a mass number. When carbon-14 releases a beta particle that is an electron, in order to complete this reaction, or in order to understand what isotope it transmutates or changes into, check this out. You need to find a number that plus minus 1 adds up to 6. So what number minus 1 is 6? 7. So you write 7 here. And then you need to find a number up here that plus 0 adds up to 14. So what number am I going to write over here? 14. Okay? So now that I know that 7 is the atomic number of the new element, I go to the periodic table, I find what's the atomic number or what's the element that has an atomic number of 7, and I find out that is nitrogen. Okay? So again, what has happened over here so that we actually explain what we have on the slide over here? What's going to happen is that the mass number is going to be the same, and the atomic number, which is this one over here, is going to increase by 1. So remember, on the alpha decay, the mass number is going to decrease by 4. The mass number is going to decrease by 4, and the atomic number was going to decrease by 2. So in the beta decay, the mass number stays the same, and the atomic number gains 1. All right, so the third type of radioactive decay is called positron emission. And the positron emission is represented in two ways that are exactly the same. One could be as a beta positive particle, and the other one is going to be like a positive electron, okay? That is a positron. So both of these representations of the positron emission, beta positive or this one over here, are valid. So what is a positron? It's a particle that has the same mass as the electron, but it has a positive charge, okay? All right, when a positron is produced, that's gonna change a proton into a neutron, and that's gonna generate, or that's gonna cause that even the mass number stays the same, but there's gonna be a decrease by 1 in the atomic number. Example, if we have the isotope of carbon 10, here, okay, and the carbon 10 is releasing a positron, what's going to happen is that the carbon 10 is going to transmutate into boron. And what's going to happen? Well, as I told you before, the atomic number is going to decrease by 1, and the mass number is going to stay the same. Why is it decreasing by 1? Because if you check this out, 5 plus 1 equals 6, and 10 plus 0 equals 10. Okay, so remember that the atomic number and the mass number initially and finally should be the same, or should be conserved. And finally, we have the gamma radiation. And the gamma radiation is just no more than high energy electromagnetic radiation, okay? The gamma radiation is not a particle, and it does not have any changes in the number of protons or the neutrons in the atom, okay? The gamma radiation is represented as this, like the gamma letter, and it's represented as this when you have it in a nuclear reaction. So gamma radiation, again, is a high energy electromagnetic radiation, and normally it comes with other types of radiation. So in this case that you have the uranium over here, it's going to release gamma radiation as well as alpha radiation, and it's going to transmutate, this uranium is going to transmutate to thorium, okay? So because of the alpha, 2 plus 90, 92, okay? So because of the alpha, it's going to lose 2 units in the atomic number, and it's going to lose 4 units in the mass number, because 234 plus 4 is 238. But again, the gamma radiation itself does not change the protons or the neutrons. So it's just additional very high energy electromagnetic radiation that is being emitted. And again, this is so high that it really penetrates through so many materials, and it's very dangerous. What are the applications of radioactive decay? There's a ton, and a lot of them are not negative. They're actually very positive, and they have helped us evolve and develop a lot of scientific research and in medicine and in science in general. So one good example of how we use the radioactive decay, it's in medicine, nuclear medicine, and it's the PET scan. I don't know if you're familiar with the PET scan, but the PET scan is the positron emission tomography, and it is used what they do is they use a radioactive tracer, okay, and that is going to undergo the positron emission. The positron emission is what we just learned, the beta positive radiation. and at the same time, it will detect the gamma rays. So the PET scans, what they do or what they're used for is to actually describe the brain function, and therefore we can actually describe if we have a cancer or we have cells that are like causing cancer in our body. There is a video that I am going to be posting on how a PET scan works that is pretty cool and it's very easy to understand. So I'm going to please ask you to check that out in Google Classroom. Okay, so we're going to see multiple examples here to understand how nuclear reactions work and also how we can find out what is the species or the isotope that another radioactive isotope transmutates into, and so on. So the first example says, write the balanced nuclear equation for the following carbon-11 producing a positron. So the first thing that you're going to do is, it says that you have carbon-11 here, right? So carbon-11 is going to be the first thing that you're going to write as the reactant in this nuclear equation. So you write 11, 6, carbon. And now it's saying that the carbon-11 is going to go or undergo positron emission. So remember, a positron is a positive electron that looks like this, okay? So what you do is you draw an arrow, okay? You first write the carbon-11, then you draw an arrow, and then you have the positron here. So, and you write the positron. So you write a plus sign, and then the positron, 0, 1, E. And now you say, okay, what number plus 1 equals 6? So that number is 5. And what number plus 0 equals 11? So that number is 11. So what you do now is you go to the periodic table and you find the element that has an atomic number of 5. And that's going to be boron. Next one. Again, write a balanced nuclear equation for the following. And it says the iodine 131 produces a beta particle. So what you do is you first write the isotope that you're given. So you write iodine 131, and 53 is the atomic number, and then you write the arrow that yields and then produces a beta particle. So a beta particle, remember, is a 0, -1, E. It's an electron, okay? So what you do is you leave a space and then you write plus and then you write that beta particle, -1, E. So now you wonder and you think, okay, what number plus -1, so what number -1 equals 53? So that number is going to be 54. And what number plus 0 equals 131? So that's going to be 131. So now you go to the periodic table and you look at the element that has an atomic number of 54 and you realize that that's xenon. And that's it. This is your nuclear equation. All this is going to be your nuclear equation. So here we have another nuclear equation, and here what they give you is actually the particle that is being emitted in the original radioactive isotope, okay? So they give you thorium over here, and they tell you that an alpha particle is released. So how do I know that this is an alpha particle? Because this is a helium nucleus, okay? This is an alpha particle. Okay, so what I have to find here is actually the isotope this thorium transmutated into. So what do I have to do? Adding again, which is pretty simple. What I have to figure out is what number plus 2 adds up to 90. So that number is going to be 88. And what number plus 4 equals to 130? So what number plus 4 equals 230? So that's going to be 226. And now I go to the periodic table. I have it over here now. I go to the periodic table and I say, okay, what number in the periodic table, what element in the periodic table has an atomic number of 88? So that's going to be radium. So Ra. So you go ahead and you write over here Ra, because this is the number, the atomic number that determines what isotope we're talking about. Next one. Now you need to know what is the original radioactive isotope. So you go ahead and say, okay, if the products, the alpha particle and the transmutated atom, they have two atomic numbers that add up to 88, because 2 plus 86 is 88. And if the alpha particle and the transmutated atom have two mass numbers that add up to 226, now I go to the periodic table again and I look at the element that has an atomic number of 88, and that element is going to be, again, that was the one that we had before, radium. Okay, so here we have more problems that we need to solve, more nuclear equations, but it's almost always like the same, okay? So we have an isotope over here, technetium, that has an atomic number of 43 and a mass number of 99. So what I do is, what number plus minus 1, so what number minus 1 is 43, that's going to be 44. And what number plus 0 equals 99. So again, I go to the periodic table, I find the element that has an atomic number of 44, and we see that that element is going to be the ruthenium. So I go back to my slide over here, and what I have to write here is going to be Ru. Okay? Now, we have aluminum. This one is more complicated. We have aluminum 27 with an atomic number of 13 plus something will yield into the transmutation, which is sodium plus an alpha particle. So what is it that we're adding to the aluminum to cause this reaction to happen? This one is more difficult, so I'm going to tell you. What we're going to do is we're going to bombard the aluminum with a neutron, because the neutron has a 1 as the mass number and a 0 as the atomic number. So now check this out. 11 plus 2 equals 13, so 13 plus 0 equals 13, and then 24 plus 4 equals 28. So 27 plus 1 equals 28. So the particle that has been bombarded here is a neutron. We're bombarding the aluminum with neutrons so that it releases alpha particles and it becomes into sodium. All right, next one, it's easier. Which element was originally the isotope that is releasing an alpha particle to become into this new isotope? So this is what you need to do. 2 plus 81 equals 83. And 4 plus 208 equals 212. So you go to the periodic table and you find the element that has 83 as the atomic number, and that element is going to be bismuth. Next one, you have the potassium here, and you're missing the atomic number, and then you see that the potassium is releasing a beta positive particle, so a positron, to transmute it into something else. So before we do anything else, we need to figure out, first of all, what's the atomic number of the potassium. So we go to the periodic table, we find potassium is here, and we realize that potassium has an atomic number of 19. So 19 is going to be the number that I write down here. Okay, that's the atomic number of protons. Even though on the periodic table it's on the top, we always write it at the bottom. Now we know that potassium is releasing this this positron to become something else. So what's that something else? The new isotope has to have an atomic number that plus 1 equals 19. So that number is going to be 18. 18 plus 1 equals 19. And then the new transmutated isotope is going to have a mass number that plus 0 equals 37. So obviously it's going to be 37. I go to the periodic table, I look at the element that has an atomic number of 18, and that happens to be argon. Two more. So then we have uranium here that is going to transmute it into thorium, but what is it, the particle that was released over here? So in order to know what the particle released was, we need to figure out what happens to the atomic number and the mass number. So what number plus 90 equals 92? That's going to be 2. And what number plus 231 equals 235? That's a 4. So what particle out of the radioactive decay that we've learned has 2 as the atomic number and 4 as the mass number? That's going to be a helium nucleus. And a helium nucleus is what we call an alpha particle. And finally, we have potassium that is transmitted into argon. And again, we want to know what's the particle that was being released here. So what number plus 18 is 19? 1. And what number plus 38 is 38? 0. So what unique and only particle has 1 and 0? That's going to be the positron. So that's the particle that has been released in this case. Often when we have radioactive decay, it just doesn't happen within one reaction, one nuclear reaction. It actually happens like a chain reaction. And this is what we call the radioactive decay series. Okay, so the radioactive decay series is a series of nuclear reactions that begins with an unstable nuclei, so in this case it begins over here, and results in the formation of an unstable nucleus. So the initial unstable nucleus transmitted into another nucleus by releasing, in this case, alpha radiation. Then this nucleus that has been formed, or this new isotope, is still radioactive, so it transmits into another one, in this case, releasing beta radiation. Then this one is unstable and does the same. It releases beta radiation to form another one, and that happens so and so, like it keeps happening until we reach a point where the last isotope that is formed or created, it's an stable isotope, which in this case would be the lead. Okay, so the example that you have here is actually the same exact example that you have on the worksheet to work. So I'm not going to do it over here because I'm going to do it in the worksheet, okay? I want you to actually do this activity so that I train yourself in understanding how the radioactivity works and how the radioactive decay works and how the radioactive decay series happen. I'm just going to guide you a little bit so that you understand how to do this problem, and then I want you to do it on your own. We will correct it on the worksheet. So this starts here with the uranium-238, which is an unstable isotope. So the uranium-238 is going to transmit it into thorium over here. So what do we see? What we see is that the atomic number has lost 2 units. So the particle that is being emitted in the meantime, and not in the meantime, in the process, is going to have an atomic number of 2. And then the 238 is going to transmit it into 234. So the particle that is being changed over here, or it's not changed, the particle that is being emitted over here is going to have a mass number of 4. So what's the only and unique particle that has these characteristics? That's the helium nucleus. And what is this particle? This is the alpha particle. Okay, so now that we have thorium, the thorium is going to turn into palladium. What has happened now? The atomic number has increased by 1 and the mass number has stayed or is staying the same. So what is the particle that has been released here? The particle that plus 91 equals 90 has to have a mass number of -1. And the particle that plus 234 equals 234 has to have a mass number, and the other one was the atomic number of -1, a mass number of 0. And this is going to be the electron or the beta negative emission, and so on. So give it a try, do this on your own, and we will correct this on the worksheet. The last section of this set of notes is on nuclear fission and fusion, which are very popular topics in the news and in general. So what is the difference between fission and fusion? Well, nuclear fission, as the word says, it's the breaking apart of a nucleus of an atom, okay? And the nuclear fusion, it's the binding together of the nuclei, okay? In both cases release large and very large amounts of energy, but one is more dangerous than the other one, and one is more costly than the other one. So the nuclei, remember, the nuclei that undergo fission or fusion, they do that because they're unstable. So the goal is to gain stability. Okay, so these processes happen always because we have an unstable nucleus that wants to get stability. So that's why they undergo either fusion or fission. So the nuclei that normally undergo fission are going to be the nuclei that have a mass number that is bigger. Okay, so bigger mass numbers, you see that over here, are the ones that are going to have to break apart and release that energy in order to get more stable. And the nuclei that normally undergo fusion are going to be the ones that have a smaller atomic numbers. So they're going to fuse together to go through this process in order to form a more stable isotope. So that's going to be for the fusion, okay, for the ones that have smaller mass numbers. Okay, so let's start with fission first. So the nuclear fission, as we just said, is the splitting of large nuclei. And when we say large, we're referring to high. Large means that they have high atomic numbers, okay, like big fat nuclei. Splitting the large nuclei into fragments in order to gain stability. That's always the goal, okay? So the energy that is being released in this process, it's a measure of the binding energy of the particles in the nucleus, okay? So the energy is high means that the particles are strongly holding together. So the energy released is a measure of the binding energy of the particles in the nucleus. Now, we need to know when we talk about nuclear fission that the sum of the nuclei, okay, or the sum of the fragments all together that have been formed, it will always be less than the mass of the original isotope that was radioactive. So that difference in mass is called a mass defect. It's the difference in mass between the nucleus and its component nucleons. So again, when a radioactive isotope goes or undergoes nuclear fission, it breaks into smaller nuclei. If we actually add the mass of the two smaller nuclei, that mass will be smaller than the mass of the original atom or the atom nucleus. So what happens is that mass is going to change into energy, and that is the energy released in the process, okay? And that is explained through Einstein's equation that shows the relationship between energy and mass. I guess that you are familiar with these two pictures, okay? So what happens in the nuclear plants of the reactors is exactly that, it's nuclear fission. The other very famous reaction related to radioactivity is nuclear fusion. And that happens, for example, in the stars, okay? So nuclear fusion, it's actually the combining, it's the opposite. It's the combining of light or small atomic nuclei. That means that they have low mass atomic numbers, okay? For this process to happen, the fusion is going to require very high energy. So that's why nowadays it's very difficult to provoke fission in our planet, okay, in the earth by humans. It's still something that is in the process of actually happening, not happening, it's in the process of being commercialized. So the energy that is required, as I was saying, is very high, and it's very high because it needs to initiate and also sustain the reaction, okay? And why does it have to be higher? Why is it high? It's because there's a lot of electromagnetic repulsion that is going against that, okay? So that's why we need an initial very high energy to start the process. That's why it's very expensive and very costly and very difficult to attain. Now, what happens in the process? What happens is that the mass of two small nuclei is combined and it forms a larger nucleus, okay? Again, what happens is that the mass of the new nucleus that has been formed, it's smaller than the sum of the original nuclei that were originally there. So the mass defect is going to change into energy, and that is the energy that is released in this process. And these are a couple of videos on nuclear chemistry that I will be posting in Google Classroom as well in case you want to review or see additional information.